on which at 2 points a set of forces are acting. The resultant of these forces are, let's say, R1 and R2. Then this R1 and R2 must lie on a plane or must be coplanar, and they must be collinear, that is, their line of action must be same, and they must be equal and opposite. So that is the condition for equilibrium. Obviously, mass of the member, self weight, etc. dot are neglected. All right. So if all these things are neglected, then the member doesn't bend. So what happens? There is no couple moment acting on this one. Member cannot bend. It can only deform axially. All right. So unless you have a couple moment, if you have some arbitrary forces, let's say some direction acting, then you will get a resultant couple moment. The member can bend. You have the bending moments also. Member can bend, but it will not remain in equilibrium. So we will consider the simplest case. Examples of these are simple spring. Spring is a two-force member, damper is a two-force member, etc. You cannot have a spring bending. Spring forces are always like this and this. You cannot say the spring bends. All right, spring cannot resist bending. Of course it can, but we neglect it. It is a very small bending stiffness, so we neglect it. So I will model a generic two-force member. Some arbitrary two-force member is there. Let's say some arbitrary two-force member is there. It is represented as a spring and damper. This is axial stiffness and damping. Damping. Here is one part. Here is one part. In general, those will be revolute joints in a planar mechanism. In a spatial mechanism, those will be spherical joints. So these are two ends where forces will be applied, and they must be revolute or spherical joints. Let's say this one's velocity is x1 dot. This one velocity is y1 dot. Somewhere xy coordinate is there. This one's velocity is x2 dot. This one's velocity is y2 dot. Obviously, position we know is x2, y2. This one's position is x1, y1. And the length of this member at any point of time is L. So L is the distance between two ends. The coordinates of two ends are denoted as x1, y1 and x2, y2. In that case, we can write a simple kinematic relation or geometric compatibility relation. What we have? L square is x1 minus x2 square plus y1 minus y2 square. Let me include z1 and z2, though they are same here. Z1 minus z2 square. Okay, so let's say x, y, z, all coordinates are there, then this will be length. If this is length, take d by dt of both sides. What will it give us? Twice L dot is equal to twice x1 minus x2 into x1 dot minus x2 dot. Then twice y1 minus y2 into y1 dot minus y2 dot plus twice z1 minus z2 into z1 dot minus z2 dot. So this is the relation we will get. Here L is not constant. L can change with time. So in this relation, of course, we can take out 2 from both sides and we can write our constraint L dot is equal to x1 minus x2 by L, x1 dot minus x2 dot plus y1 minus y2 by L into y1 dot minus y2 dot plus z1 minus z2 by L, z1 dot minus z2 dot. That is one way of writing, or you can change these signs. You can write x2 minus x1 by L into x2 dot minus x1 dot plus y2 minus y1 by L into y2 dot minus y1 dot plus z2 minus z1 by L into z2 dot minus z1 dot. So as you like. This, as you understand, is same as cos beta x2 dot minus x1 dot, that is relative velocity x2 dot minus x1 dot plus cos, sorry, that is cos, not beta, cos alpha. Cos alpha, cos beta y2 dot minus y1 dot plus cos gamma z2 dot minus z1 dot. That is projection of relative velocity to L direction. So you have two ends, between them you have some relative velocity x2 dot minus x1 dot I cap, y2 dot minus y1 dot j cap, z2 dot minus z1 dot k cap, and you project it according to your cos alpha, beta, cos gamma. These are direction cosines, of course. These are direction cosines. So you just project them to that direction of L. So very simple. Okay, relative velocity is projected to the direction along direction of the axis connecting the two ends. Now this cos alpha, cos beta, cos gamma, as you know, when you take moment about an axis, the unit vector can be taken. Let's say an axis is defined by AB points. Unit vector can be eta cap AB, or it can be in the direction BA. Likewise, whether you take x2 dot minus x1 dot, you will get some cos alpha. If you take x1 dot minus x2 dot, then that alpha will change by 180 degrees. All right, not alpha, the L direction will change by 180 degrees. Accordingly, alpha, beta, and gamma will change. All right? So it doesn't really matter whether you take point 1 to point 2 as your direction of L or point 2 to point 1. It doesn't matter. Accordingly, you will change how you take the relative velocities. So you might choose to take x2 dot minus x1 dot. You might choose to take x1 dot minus x2 dot. It's all the same. So this is very basic. That is our constant or kinematic relation. And I will just rewrite this for planar case. This is the general case. For planar case, we will just remove the last term z2 minus z1 by L because that's 0. L dot is whatever you like, x1 minus x2 by L. Dot. So that's very simple formula. This is the kinematic relation that we will use to model a lot of systems. So if this is the kinematic relation, the forces must as well transform accordingly, because we know our all constants 1, 0, transformer, gyrator, all those things are power conserving. There is no loss of power there. So if you represent kinematics correctly, forces will also accordingly represent correctly. So as the first step, let me model something very simple. Let's say I will keep this relation here in the view. Let's say we model a system like this. There is a block of mass connected by a spring and damper, and this mass is resting on frictionless rollers. So put some K R. Let's say K1 R1. This is, let's say, M1. And there is a revolute joint here, from where we have a pendulum rod hanging like this. So let me draw it somewhat like this. I have drawn it like this because I do not want my spring and damper to bend. So these are rigid. And massless. Whatever stiffness and damping extension will come from the spring and damper. This basically represents a simple rod. So any kind of simple rod. This is equivalent to a simple rod. Simple thin rod. Okay, having some axial flexibility with axial flexibility.
Sir,
Yes.
In Hooke's law,
Yes.
the damper is not taken into account, right?
It's there actual the stress is E times epsilon, okay? Plus there is another term called lambda times E times epsilon dot. This term is called Rayleigh damping or beta damping.
Okay. Yes.
So that damping is there. Okay. any material, or then if you hit a steel rod, it should continue to oscillate for infinite time. If you take it to space, no air, then it should be continuing to oscillate. Rubber string, if you try to, let's say, pull it and release it very quickly, so you will see it heats up. That
Yes,
heat
sir.
is coming from the strain rate. Okay, so it's dependent on strain rate as well. Okay.
Actually, the thing is, so far when you have studied stresses, it has always been that the material has come to equilibrium. All the stress that you have done so far is actually that means that the force has been applied over a considerable period of time. Everything has settled down. This is the first time you are doing something where things are not settled down. They are moving.
Okay, thank you, Kingsu.
So it's like equilibrium thermodynamics or non-equilibrium thermodynamics, kind of.
Okay, kind of. All right.
Yes.
Okay, we are doing everything dynamics. Okay, if the system doesn't move, then what are we controlling? Okay.
Yes, sir.
Obviously, our system moves.
Yes.
Can I interrupt once more, Samudra?
Yes.
If you again recall, if you are sitting on a chair, a particularly soft sofa, what you have been taught in all your courses on solid mechanics is what happens when you have sat down on the chair or sofa for around 5 minutes time. That is the stress that you have measured in those courses. But if you recall, there was something called impact. So you got a different kind of stress there. But that was also, I mean, like at the point of maximum impact. But here we are considering all the intermediate points. Stress is developing, reaching a maximum. Again, it will come down. Again, it will reach a maximum and so forth. So this is slide. That is why we have that extra term. This is dynamic stress.
Yes, sir.
Yes. So there is another term also, which is, this is lambda times E. This is called stiffness proportional damping. And there is another term called mass proportional damping, which is also called alpha damping. Here, because we have assumed this rod to be massless, we are neglecting that alpha damping term. The actual damping, total damping, Rayleigh damping has a beta component proportional to stiffness and an alpha component that's proportional to the mass of the body. So we are neglecting that alpha component because we are considering our mass only at the pendulum. So let this pendulum have a mass, let's say M2. This stiffness, let it be K2. This damping be R2. So to model this, what we will do is that we will set some coordinate system first. So let's put some kind of coordinate system. So let's say somewhere some global coordinate is there. So this one's position is, let's say, x1, y1. This one's position is, let's say, x2, y2. Gravity, of course, acts downwards. All right. So, okay, what we do is, okay, we basically have, I will put one x1 dot. All right. Another junction for each x1 and y1, okay, and x2 and y2, I will put separate junctions. Somewhere else I am putting one y1 dot. So this is velocity of big mass. To this I connect the big mass M. To this I connect, this is not moving, so I connect source of flow 0. I have seen in your assignments, some people put source of effort, gravity, in x direction. I have seen interesting bond graphs. Everywhere mass is there, there is weight. No, okay, it has to be only in the y direction. And here, because y direction we do not have motion, that block is constant in y direction, so we can remove this y1 dot junction afterwards. So right now I have kept it. So this is one junction. Then the second one is 1 x2 dot, that is for the hanging mass M2, where we have mass M2, and here 1 y2 dot, where we have of course mass M2, and we have the weight. Okay, so these are the junctions set up. Now what else is there at x1 dot? We have a spring there, we have a damper there. So that's for the horizontal motion of the block. So now these two, the block and the bob of the pendulum, they are connected by the rod, and this rod is a two-force member, because one end of it you have a point mass where acceleration related pseudo force and the weight of the body act as a point, that is x2 y2, and at the other end you have a revolute joint. Whatever forces come, they act at that point only, that revolute joint only. So we have a two-force member. The weight of the rod is neglected. Weight as well as mass of the rod is neglected. So we will do that same kinematic relation. Okay, let's take x1 dot minus x2 dot. How? Zero junction. So here it is x1 dot, here it is x2 dot. We have x1 dot minus x2 dot. We could have taken x2 dot minus x1 dot. It's fine, no problem. But it should not be, the power direction should not be such that it becomes x1 dot plus x2 dot. Okay, it has to be either x1 dot minus x2 dot or x2 dot minus x1 dot, one of these. Then of course we will put a transformer. According to the relation, kinematic relation, if we have x1 dot minus x2 dot, then it has to be multiplied by x1 minus x2 divided by the length. All are time varying quantities. x1 is not constant, x2 is not constant, length is also not constant. All are time varying quantities. So that's done. One part. Likewise I do y1 dot minus y2 dot. Put a transformer. This is y1 minus y2 divided by L, and I add them up. So what do I get flow here? Here it is x1 minus x2 by L times x1 dot minus x2 dot plus y1 minus y2 by L times y1 dot minus y2 dot. Basically this is L dot. So I put here L dot. This is same as L dot. So what we have done? We put all masses and weights and everything, okay, at different one junctions. We took relative velocities in x direction, we took relative velocity in y direction, we took their components along the direction of the length, so that we got L dot. L is not fixed, the direction also is not fixed, because direction is also changing, length is also changing. So we have L dot. At L dot, we have the flexibility of that rod. So we have a stiffness. What is the stiffness of the rod? It is area into Young's modulus divided by the length. You know, delta or elongation of a rod is FL by AE. So from that we get F by delta is equal to AE by L. So that's the C element. And we also by damping. Let's put that proportional damping, some parameter lambda times AE by L. this E and L, sorry, lambda are material properties. For steel, we will take 200 to 210 GPa, and lambda is 0.002 to 0.003. Right. Its unit is second inverse. Its unit is second inverse. Okay. So this is the material property. You have different material properties for different materials. So whatever material you choose, aluminum, copper, or whatever, you will get these values. So this is very simple model. Now, in order to compute this model, of course, we understand this thing can be removed. At this junction, flow has become 0 because it is one junction, flow has become 0. So this is entirely powerless. This, and this are all powerless. We can remove them. But for similarity, we will keep them. It gives a structure. So what else is needed? We see that these transformers are using the value of x1, x2, y1 and y2. So if transformers are using these values, we must also get those values from our model. We do not have anything, we will get directly x1 from this. X1 we will get from this state. But we have nothing to get x2. We have nothing to get y2. So we will add some sensors, some virtual sensors to this model. So that using those values, we can define this transformer modulus. So I will add some sensors to this. So let me add something here. You can add DF. I have written in my convention flow activated C. 2C. This one we know, we do not require. This one we also have. So we do not require. This one is 0. And this one whatever you require. So we added 2 sensors. If you want, you can add, no problem. So if you want, you can return it and add it. Okay, these 2 are not required. X2 dot and Y2 dot we obviously require. So using these values, this gives X1. This gives X2 dot and also X2. So those values will be used. In TF. Okay, so those values will be used. I do not put another sensor for L because I can write L in terms of x1, x2, y1 and y2. So I don't require. If you require, you can add here. It's not a problem. So is this modeling clear? Students,
Yes,
is
sir.
the modeling clear?
Yes,
okay. So zero junction to take relative velocity, then multiply with whatever factors and produce L dot. If it is 3 dimension, you will take x1 minus x2 dot into this transformer, y1 minus y2. Similarly, another 2 pairs will appear, z1 minus z2. All of them has to be added at the zero junction. So now, this simple model, we can extend it to model a double pendulum. And we will model the double pendulum exactly same dynamics we will model as it is there in, let's say, Wikipedia.
So,
let's
sir,
see.
since the source of flow is 0 on the block,
We can remove
no,
that.
no. So why are we measuring with the C? Like,
No, I told if you want to retain that source of flow, you can put something. Okay. If you return it, let's say we will have a modular structure. Okay. If you have n number of such pendulums hanging, then why you make some part of model simpler? Okay. Let it be copy pasted. I will show you how we copy paste. Okay. So you see here a double pendulum, right? It's making some kind of a motion. This is the one we will simulate. Forget about this, some bifurcation diagram. This is the path of a double pendulum when an LED tracer is kept at its tip. Okay, so it will make, if it is moving at high speed, it will make some kind of a thing like this. You take measurement at high speed camera and play it slowly, or if it is slow speed, you take measurements at certain time instances with a time gap and then play it very fast. You will get some kind of a situation like this. And this double pendulum, how can I pause this? Okay. This double pendulum is also chaotic. If you start from same position with little bit of difference in initial conditions, you will see the response diverges. Right. So you start with almost same location, a little bit of difference, you will see the response becomes completely different after a short period of time. That's what says it is chaotic. It is dependent on initial condition, and it will never come back to same state again. Anywhere in its complete infinite time you run, it will never come back to same state. And same state means not just a position. Same state means same position, same velocity. Okay, for all the variables, same position, same velocity, it will never come back. If it comes back, then it has repetition, because wherever you started, if it comes back to that point, then onwards it will exhibit exactly same behavior as it did in the starting. So that means it will have a periodicity. So we will model this one. It doesn't take much time to model.
Sir, yeah,
Yes.
here the transformer constants are not actually constant; they are also
No, they are
variable
not
with
constant.
time.
It doesn't matter. Okay. See, what happens if you have a transformer? You have a relation that flow are scaled in certain way, efforts are scaled in certain way. Then from both sides that constant vanishes if you do a power balance, as long as that is true for all time. So that constant need not be that that may not be a constant. Okay, that is true for all times. Let's say f1 f2 is equal to mu f1, right? E1 is equal to mu e2. Right? We multiply them. Okay, so you have mu e1 f1 is equal to mu e2 f2. That is true at all times. Right? True at all times. So you can remove that. Mu can be mu t. Right? Mu can be mu function of time, mu function of state variables. It can be anything, doesn't matter. Okay, you can remove it. Okay, so that transformer and gyrator modulus may not be constant. So that's what we are doing. We are trying to model a very highly nonlinear system. Okay, and it's a pendulum not having small motion with, okay, you have sine theta approximation to theta. No, nothing. It's full pendulum. It can rotate full circle. All right. Okay. So we have a pendulum somewhere. Let me put my origin here for simplicity. So my origin is here. This is my x naught, y naught point. From there, I have one mass, m1, then another mass, m2. Let this be x1, y1. Let this be x2, y2. All right, very simple thing. So how do I model? I model it simply like this. Okay. I have one x0 dot, which is source of flow is to 0, doesn't move, the pivot point. So you don't require inertia, you don't require flow sensor. We have one y0 dot, exactly identical, source of flow is equal to 0, no sensor required, it's 0 0. Then one x1 dot, whatever way you want, x0 minus x1 suppose, y0 minus 1 y1 dot. Take transformer x0 minus x1 by, let's call it L1. This is L1, this is L2. Take that transformer from this side, transformer y0 minus y1 by L1. Add them up, first pendulum stiffness and damping. That pendulum rod's stiffness and damping, C is to, let's say area is same, Young's modulus is same by L1 to lambda times AE by L1. So this is first pendulum model. Now the second pendulum is a first pendulum like thing, but its base is moving. Second pendulum is hanging from first pendulum. So it's exactly repeated model. Exactly repeated model. 0, 1 x2 dot, 0, 1 y2 dot, transformer x2 minus x1 by L2, transformer y2, this is y1 minus, okay, I have to make it correct, this is wrong, x1 minus x2, okay, as per my power direction, x1 minus x2, if you are done reverse power direction, it will be x2 minus x1. So y1 minus y2 by L2, add them up, you have 1 L2 dot, this is L1 dot. Again here stiffness AE by L2 is equal to lambda AE by L2. Simple thing, add inertias and weights equal to M1, I is equal to M2, I is equal to M1, source of effort is equal to minus M1G, source of effort is equal to minus M2G, I is equal to M2. That's it. That is the best model. Model is done. To define these transformers, we have to measure the values of x1, x2, y1, y2. x0, y0 are known, they are constant. So I will simply put those sensors. So let me put my sensors. Flow activity. Let's see. These are all displacement and flow sensors. If you causal this model, there is absolutely no problem with this model. No loops, nothing. It's very, very good model. Start with source of flow. This anyway can be removed. So what else we have? Source of effort. Nothing happens. Start with one I element. This will come here. Start with this I element. This will come here. Okay. Then this zero junction must come here because no strong bond is remaining. Extend it through transformer like this. Then this zero junction connected to L1 dot. Two bonds are caused away. So you have to put strong bond. Once you put strong bond at one L1 dot junction, then other two are weak bonds. So it's done. Likewise, we complete the other side. So all are perfect. There is no problem. Everything is done, causal. We don't have to go for R elements or internal bonds. No causal loop, no algebraic loop. Perfectly fine. Very good model. And it will run very fast. Very, very fast. So what I will do is I will model this in symbols. Okay. And we will start with the configuration. Initially, this was straight. Initially, this was straight. This is, let's say, 1 kg. This is, let's say, 0.1 or 0.5, whatever you choose, whatever value you want. What value I have chosen here? 0.1 kg. 1 kg. This Young's modulus is known. This rod's area, both the rods, area is 10 to the power -5 or -6, let's say. So 1 mm square kind of thing. This is 1 meter length. This is meter square. And this is, let's say, 0.5 meter. So if you take rho is equal to 7850 kg per meter cube, this rod's weight will come to something around 7.8 grams, and this will be around 3 grams. Okay. So we can neglect them with respect to the mass of the bobs and other things. We can assume those to be massless. So this is the initial configuration at t is equal to 0. All right. So at t is equal to 0, this one x1 is equal to 0, y1 is equal to -1. Here x2 is equal to 0, y2 is equal to -1.5. At t is equal to 0. These are our initial conditions. All right. And we will push this or this with some velocity. To start the pendulum, we will give some initial push. So is it understood, students? Can I move to software?
Sir, that AE by L constant,
Yes.
we will put that a very big value, right, sir?
It is.
So, sir,
Uh,
but
if
that
you
comes from physical consideration that the rod can be slightly extended or it can be
very
treated as
slightly, very
spring.
slightly with
Yes, sir.
with this load, So let's say 1.1 kg, the top rod will extend by about 0.006 or 7 millimeter. Okay.
Yes, sir. But that comes from physical consideration that we can treat the rod like a spring. But what if we
Yes.
want to mathematically model something which cannot be extended? So,
Then we have to model these as rigid bodies, not as massless pendulums. We can model these as rigid bodies and implement those constants. We have to put the constraint that velocity at, let's say, the second pendulum is a rigid body, or first pendulum is a rigid body. So that rigid body has 3 degrees of freedom. Initially, it has 3 degrees of freedom. Then we will constrain it. We will say that the velocity at the root of that is 0. Okay. So that constant we will implement, and 2 degrees of freedom will be removed, 1 degree of freedom will remain. Likewise, the second pendulum we will take as a rigid body with 3 degrees of freedom, planar motion, x, y, and rotation, and from that we will find the velocity of the fixation point, that is the point connected to mass m1, and we will then say this velocity is same as the velocity of the tip of the other pendulum. Okay.
yes, sir. That theoretical part is clear, sir. But how will we connect this x and y components of the velocity in this bond diagram if it is a mathematical object?
Oh, how will we connect these things? We will put a constant, they are same. We will say they are same. Okay, that is our constraint. If time permits, I will do that. Okay, how to model any general mechanism, let's say slider crank mechanism, 4-bar mechanism. Okay, this is an open kinematic chain. Okay, so those are closed kinematic chains with same kind of principle, and that doesn't require that I have a rod which has even low mass. It can be any rigid body. Right. Okay. Now this rod is treated as a flexible body. We can treat that as a rigid body too, but that will be based on a different modeling philosophy. All right.
Yes, sir.
So if time permits, or I will send you a document, okay, book chapter from where you can read it. So I will go proceed and model this in symbols. You already know how to model. So I will just model it very quickly. I will specifically show you how to model the transformers and these sensors. That's it. Okay. Yesterday we have done sensors, but this transformer and how to give their transformer orientations, that thing I will show you. So, oh, symbols is not there. So I go to bond pad. I create my models. I am doing very fast. Source of flows, two source of flows I put. Two one junctions I put. These are zero. Okay, things. Okay. Then you have two zero junctions between two one junctions. Another one junction. So first part of the bigger pendulum I am creating. Then you have a transformer. Here also transformer. These two transformers connect to a zero junction. So let me drag these things closer. So zero junction. Then I have one L1 dot. Here we have spring damper. Then we have inertia here, source of effort here, and a sensor. This is half the model structure. Half of the model is drawn. Then what I will do, I will copy this part. I have selected this arbitrary marker. I will copy this part. So I have copied, edit copy, edit paste, Control C, Control B. So let's put it here. Fine. Okay. So I can drag them also. So that is.
Sir, with what did you select that line? I mean that enclosure.
Enclosure here. At the top there is after the shape sign rectangular mark. Then there is a preform mark. Did you see at the top? New, open,
Yes, sir.
shape,
Yes, sir.
rectangular, that preform. I didn't choose rectangular because if I do it, these two SFs will also go. I don't want those two SFs. So I connect these three, these two. One junction has come by mistake. Okay. Anyway, I delete it. So this is done. This is my model. Let's center it. Looks good. Fine. Everything is fine. Okay. So number it, power it. Now we will check power directions are correct or not. So this zero junction difference is taken. This zero junction difference is taken. Here also it's fine. The two transformers are coming to zero junction, adding. Fine. So this power direction has come according to our picture incidentally. It has come correctly. It may not have come like this. You have to then adjust the power direction with this power direction changer. Okay, you have to change. If required, you will change. So now you note that if you change power direction of one side of transformer, the other side automatically changes because you cannot have transformer with power direction both in or both out. Okay, so this is correct power direction. Then we will put causality and I will change my activation. Activation, this is flow sensor. Q9 is flow sensor. Then bond number 14 is flow sensor. Bond number 29 is flow sensor. Bond number 25 is flow sensor. So these are my flow sensors. Let me put them like this. Okay. 29 like this. I want these sensors to be very clearly visible to me. Okay. So that's done. Now our model in comparison to yesterday's model has some new element, that is the transformer. You can have a transformer or gyrator. So after you have done this, you have to give the transformer modulus. To give transformer modulus, in utilities you have seizure, numbers, this power direction changer, causality changer, activation. Below that you have an item called modulus specifier. So this modulus specifier comes as an arrow, curved arrow with a plus sign above that. So you take this plus sign and click on the transformer element for which you want to specify the modulus. So that is the only difference with respect to the elements that were present in yesterday's class. So I put modulus of this transformer. So this modulus, okay, in the modulus I cannot write an expression. Modulus is a variable. Alright. So modulus is a variable. I cannot write there any expression. I cannot even write there multiplied or something like that. Okay. Unlike the block diagram model we have done where gains could be specified as some kind of expression, here modulus is a variable. It's a C++ variable. You have to give a genuine variable name. Any acceptable variable name in C language or C++ language without space, without any kind of plus, minus, star, these kind of symbols, all acceptable variable names you can give. So this is a modulus of pendulum number 1. Let me call it mu x. This is related to x. So mu x1. Now the direction I have chosen pawn number 6 to 17. Okay, you can change it from 17 to 6 or 6 to 17. Our direction I require it should be in certain way that if you want to show that direction, you can click here, show direction, okay, and put a modulus variable name and tell OK. Okay, so this transformer modulus is mu x1. It's not shown here, but internally it's mu x1, and the orientation is shown from 6 to 17. The bottom transformer will be oriented from bond number 8 to 16. It will be from 8 to 16. So we will give it a name. Let's say mu y1. It is from 8 to 16. I will put show direction. So that's done. Likewise, 22 to 31 we will have a transformer. Let's call it mu x2. Show direction. And 24 to 30, let's call it mu y for pendulum 2. 24 to 30, yes, it's 24 to 30. Show direction. Done. So we have specified our moduluses, moduli. If you do not do that, it will catch here. It will tell you transformer modulus not done. Okay, and it will catch you and tell you an error. And you can double click that error. It will tell you exactly which transformer modulus is not specified. So we have done this. Then we derive the equations. Some set of equations have come. That's good. We don't have to see it. Equations are correct. Now here in the expressions, source of flow 1, I will put equal to 0. Source of flow 2, that is also 0. These are the two source of flows connected to this one X0 junction. Okay, if you want, I can annotate this. Let's say this is X0 dot. This is X1 dot. This is X2 dot. This is Y0 dot. This is Y1 dot. This is Y2 dot. This is L2 dot. This is L1 dot. Fine. Okay. So our model is annotated. Once I toss that, you see my equation is gone. It doesn't allow me to derive equation till I do a check integrity, because I might have done some arbitrary changes. So I have to do check integrity. I have to rederive the equations. Once I toss the model, I have to do a check integrity. Nothing changes in equations. So we have source of flow 1, 0, source of flow 2, 0. These mu y1, mu x1, these are the parameters I will write before. The stiffness damping I will write before afterwards. This M13, where is 13? 13 is connected to x1 dot. So this is M1, mass of pendulum 1. Okay. M10, this is also mass of pendulum 1, or call it MP1. This also I will call MP1. This M1 is deleted. Then you have SC11. Where is that? Okay, that is with pendulum 1. So minus MP1 star G. Then we have another mass here, M26. Where is 26? That is a y direction mass. So that is M pendulum 2. Its weight is AC27. That is minus M pendulum 2 star G. Then you have M28, that is also M pendulum 2. Okay. So these are the basic things. These are all known things. I will drag them up. I will say, I don't want to clutter them here. I will drag them up. I will send them up. MP1, all those things, G, somewhere I put them up. This, you just click and drag, so that they will go up. Click and drag, leave them somewhere. Okay. So these are my parameters. I am left with some more parameters. So this is mu x1, mu y1, mu x2, mu y2. Let me bring them down. I want to put them at the end. Mu x2, mu y1. Where is mu y2? Mu y2. Okay. I will toss them at the end. So I have taken them up. All right. Now I have K19. This K19 is stiffness of rod 1. So what I will write? A star E by L1. So L1 is a new variable created, AE is created. R20 is some lambda star K19. We can write that lambda star K19 or lambda star AE by L1. K33 is stiffness of second one, that is A star E by L2, and its damping is lambda A33. So stiffness are defined, everything is defined. Now we will write mu x1. Now what is mu x1? Mu x1 is x1 minus x2, x0 minus x1 by L. So x0, let me write x0, or you can say it is 0 origin. 0 is not required, I have just put it. Minus x1. x1 comes from C element at 14. I will write it as Q14. So 0 minus Q14 divided by L1. That's the modulus of fast transformer here, 617. And mu y1 is 0 minus the y position given by sensor at bond number 9, Q9 divided by L1. So mu x1, mu y1 are done. Likewise, mu x2, that will be x1 minus x2. That is sensor Q14 minus sensor Q29. You see this picture, it shows all kinds of integers, numerical values, and all kinds of QP, whatever sensed variables, it shows them in red color. It will not create a variable for them because those are known to this. All right. Whereas when I wrote L1, when I wrote lambda, it created an input variable for me. For states and any constant numerical value, it will not create an input variable. So mu x2 is q at 14, that is x1, minus q at 29, that is x2, divided by length 2. And mu y2 is y1, that is q at 9, minus y2, that is q at 25, divided by L2. So that's what is done. So my model is fine, but with a problem. This L1 and L2 we have to compute. So we have to compute L1, L2. These are not constant. You can treat them as constant, but let me put them as variable for general purpose. Okay, here deformations are small, but suppose they are actual real long springs. Okay, with suppose possibly large deformation. So I will make a general model. So what I do, I find where is L1, L1. So L1, I write it as Q0, x0 minus x1 square plus y0 minus y1 square root. So square root is SQRT, C language function, SQRT is square root of, you can use POW function. There is nothing called SQR function in C language. You can use POW or PWRF. I don't use the function. Let me write it directly. So let's say Q14 minus 0. Intentionally I am putting it, let's say 0 minus Q14. Intentionally I am keeping it in explicit form. 0 minus Q14. It's not required. I could have written Q14 square plus y0 minus y1, that is Q9 star y0 is 0 minus Q9. This thing square root, that is L1. And L2, I will copy and paste this. Where is L2? L2. L2 is x1 minus x2 square or x2 minus
Sir,
x1 square. Yes.
So why are we finding the length through the flows?
Where? Which flow?
So Q is the flow, right?
Yes. No. Q is not flow. Q dot is flow.
So,
Q is displacement or deformation.
but mu you had written as so Q is the flow taken by the capacitive flow activated element, right?
The flow is F14. It is integration of that. Okay. So here square root of x1 minus x2. x1 is 14. Q14 minus x2 is Q29. 14 minus Q29. Control C. Control B. This is Q9 minus Q25. Control C. Control B. So that is L2. Alright. So we have got L1, L2. Now if you look at it, if we do not give initial conditions, then this Q14, Q9 all will be 0. This L1 will be 0, L2 will be 0. And they are appearing in denominator, and our simulation will terminate with a runtime error division by 0. So we have to give some initial conditions in our simulation. If you want to avoid giving initial conditions to simulations, you can enter them as parameters. So I will try to enter them as parameters. Somewhere before this L1, I write a statement. If, normal C language statement, FIRST underscore time. See this first time has not come in normal black color. It has come in some color, pink like color. Okay. All right. So if first time is a defined variable, that is only the code will be executed only at t is equal to 0 at the very beginning. Afterwards, it will never be executed. So this code I will write at only to be executed once. So what is it? I will say Q, what is that number? Q14 is equal to, let's say, some parameter x1, Q9 is equal to some parameter y1, Q29 is equal to some parameter x2, and Q25 is equal to some parameter y2. So that I don't have to give initial conditions, they will appear as parameters. I will give them parameters. Fine. So I have got all parameters. Okay. My model is ready. I will save it in the desktop. Let's say, let me call it my double pendulum. Create a project. Generate the sim file. As usual, compile. I don't have to set the path. It's set yesterday. So create Borderland compiler. Create, compile. Good. Zero errors, zero warnings. Simulate. So mass of pendulum 1 is 1 kg. Mass of pendulum 2 is, let's say, 100 grams, 0.1. G is 9.81. Area is 10 to the power minus 6. 1 E minus 6 is 10 to the power minus 6. E is 200 GPa, that is 2 into 10 to the power 11. 200 into 10 to the power 9. X1 is position, initial position. X1 was 0. Y1 is at minus 1. It was hanging downwards. X2 is 0. Y2 is at minus 1.5. 0.5 is the length of the second pendulum. Lambda is 0.002. Okay, so these are few parameters, not much. No initial values are required. Otherwise, you have to give it here. So it's not required. Okay. I will give an initial momentum to push it. What I want to plot? Let's plot pendulum 1 position. Q14 and Q9. Q14 and Q9. So horizontal is Q14X. Vertical is Q9. What will be the motion? Fast pendulum, its tip will move in a circle. That's it. Its tip will move in a circle. Let's simulate for some time. Let's say 40 seconds or 20 seconds. Let me put some records. 4096. This error limit doesn't matter. So this is what I will plot. So I run. Nothing will happen. Nothing is there. Why nothing is there? It's a point. We are not seeing it. We have not done anything. That thing has stayed there. So we have to push it. So what I will do is I will push the big mass in X direction. Big mass in X direction with certain velocity. Okay. So that I will give as an initial condition, momentum initial condition to this mass 13. Mass at bond number 13. So I give momentum P13 as initial condition. So whatever velocity I want into the mass is momentum. So mass incidentally is 1. So whatever velocity, that is momentum. So P13 I will give a push. Let's say I push it at 5 meters per second. Now let's see. So this is moving on an arc. Nothing has happened. It is moving on an arc plus minus 1. 1 meter is its radius, 1 meter is its length. So plus minus 1, it's making a circle, and down it is maximum minus 1. Top it is going up to 0.15. So not interesting. Let's go to...
Sir,
yes.
Could we have given this initial condition through that if first time?
Yes, but then we cannot change. We have to give it in parameter. Yes, we can give a parameter here. Okay. There we will write P13 is equal to some P dot. Okay. Px naught or something. We can give it. You can give it. No problem. Okay. No problem. We could have given it there. So what I want to plot is not... Yes.
So what
yes,
is Y8?
Y8. Y8 is
Yes.
Q14. That is state number 8. Y0 is P26. That state vector is written here in terms of Y. Okay. And because of C language convention, the array index doesn't start from 1, it starts from 0. Okay. So Y0 is first state vector, Y1 is second state vector, and so on. Okay. So Y8 is state number 14. I don't see that Y8. I see Q14. I see from here, Q14 is X position of the bob 1, and Q9 is Y position of bob 1. For the bob 2, Q29 is X position, Q25 is Y position. So I will see Q29 and Q25. So I will plot that Q29 and Q25. Q29, Q25. See this? This picture has come. Some picture, we don't understand anything from this. So if you go to that Wikipedia page, it's similar picture. Do you see this picture? This picture is similar to what we have got, okay, for some initial conditions. but we cannot understand anything from this. So what I will do is I will set up an animation for this. So animation is very simple. You can learn it yourself. So I will send these results. I will send those to some data file. I don't need time. What I require is Q9 is second state, Q14 is X1, Q9 is Y1, Q29 is X2, Q25 is Y2. So I will send this data. I will save this to some queue. So I can send it to Excel. I may not send it to Excel. So I will give a output file name. Let's call it my data one. My data one dot dat. I save it. I send it. So this data is sent. I will go to animator module of symbols. Try to see this. Where is animator? Animator module. Right. You can see the document how to do it. I will expand this, fit to current view. I will put a line from where this pendulum is hanging, some line. This is my horizontal line. I will put a point where the whole thing is, this is my origin, let's say. And at the origin, I will put lot of things. I will put a small circle here. I am drawing here, I will take it there afterwards. There is a big one, small bob, big bob. I will have a line. This line, I will draw that line. This is my bob line. But I will draw that line from that to that point itself because its two ends will come from data. So one line, I have got another such line for second thing, very near line. So second line I have drawn. I will put two tracer points. This one is tracer. I will put a tracer here. I will put another tracer here. So two tracer points. So I have drawn two lines, movable lines, two bobs, two tracer points. These bobs I drag and put here wherever I want. Okay. Now I will load my data from that my, where is it? Desktop, my double pendulum, my data one, load my data, and after loading data, the next item is object properties. So I will set this object property. I have drawn a horizontal line that doesn't move. I will not give anything. I have drawn a small vertical line that doesn't move. I don't give anything. Object 3 is ellipse. This ellipse will move. I have drawn a circle, but it's general ellipse. You give coordinates of two corners of that ellipse. So if those two corners move differently, that ellipse can expand and contract, things like that. It can differ. In our case, it's a rigid body. So we will give one corner whatever data, the second corner we will give same data. So point 1, according to my data file, wherever I have exported x1, y1, x2, y2. So point 1 of this ellipse, okay, this ellipse moves according to its x position is in data column 1, y position is in data column 2. The other end, because it is not deformation, it is same. It's not deforming, it's same. So this is my object 1. I will give it some color, maybe let's say green color, or maybe slightly dark green. No, green, it won't be visible. Object 4 is smaller ellipse. This moves according to x position stored in data column 3 and data y position in data column 4 of my data file. Point 2 also moves accordingly. 3, 4. So don't worry about test, I will do that. Okay. So this is okay. Where is my test? Predict test. Edit settings. Timing. Make it from 40. 2, 20.
30.
42, 40, okay. So 20 minutes there, plus 10 minutes and 10 minutes extra. It's fine. So done. Okay. All right. So point 2 also moves like that. Object 4 is the rod. Its one end moves according, its one end doesn't move. It's fixed to the root. So when it doesn't move, it's 0, 0. The second point moves according to data column 1 in X, 2 in Y. So that is X1, Y1 point. Object 6, its point 1 moves according to pendulum 1 motion. So data columns 1 and 2, that is X1 and Y1. Point 2 moves according to pendulum 2's motion, X2 and Y2, that is in data column 3 and 4. This tracer is, I will put a, what is happening? This tracer, okay, tracer. Tracer has only one point. This is tracer for first object's motion. This is tracer for second object's motion, 3 and 4. I can put some color. Let this be some yellow color so that you can see them. Let this be some color, let's say yellow. Something, let's say cyan, okay, so that you can see them. Okay. Okay. So this is done. This will run. But if I run it, I will see nothing is moving. That's
So
because.
can you explain once again the ellipse thing and the why you took so many objects?
Okay, I have taken one object is fixed straight line, not moving. Another object I have taken here. These are fixed. These are fixed. I don't give anything. Then I have taken one. This is M1. I have taken a small one. This is M2. All right. Okay. Then I have taken one rod L1, another rod L2. So these are objects I have taken. All right. Okay. Now these objects coordinates are given with respect to inner cell frame. Okay. So this point coordinate, this line will be drawn between two coordinates. Those coordinates are measured from the origin. So I will draw that line. I will basically put that line as a point, so that when this point moves according to x1, y1 and this point moves according to s2, y2, that line will be automatically created. So I need this. In addition, I have put some tracer. What is that tracer? You will see. The object will move. Right? That tracer actually will leave a point behind. All right, where that object was previously. That's why that tracer is there. You will see that animation is complete. So what we see here is that my motion is between plus minus 1.5 of pendulum 2. It's obvious. Length was 1, next length was 0.5. So maximum it can go is plus minus 1.5 in y direction and x direction. So this 1.5 has become there 1.5 pixels. We have to scale our results, numerical results, to screen coordinates. So unless we scale that, we will not see that motion. So that's why I will use a scaling. This scaling you have to select according to your screen resolution. So I have pretty high resolution. I will select, let's say that 1.5 I want to make 150. Then I will use a scale 100. Otherwise I will use a scale 200, let's say. So what I can do is I can specify a gain. This is scaling from numerical results to screen results. So let my scale be 200. Done. Now I simulate this, run this. Do you see something happening or it's video lag?
It's visible, sir.
So we can see.
We can see it.
So now that you see that tracer point, that yellow dots at the, our bobs have become wrong. We have set wrong data for the bigger bob. Okay, my bigger bob has become lower bob. I will correct it. Okay. So I will correct this object properties. Sorry. Where is that object properties? So my object 3 is that ellipse. That moves according to 3, 4. And this object is 1, 2. Okay. So there that graphical results were not making any sense. Now it makes some sense. So if you look at this smaller pendulum, you see it's rotating in clockwise direction, but sometimes it will rotate in anti-clockwise direction as well. Now you see it's anti-clockwise. Okay, so sometimes clockwise, sometimes anti-clockwise, never repeating whatever happened in the past. Nothing ever happened in the past will repeat ever again. You can simulate it for a long time and see this. So what I am going to do is do a different simulation. Okay. I will simply change my data. What I will do is my initial condition was 5. I will give it little bit more. Let's see if it rotates fully. Yes, with this it is rotating completely. I will run for a slightly more time, maybe 40 seconds. Right. So it's good. 40, maybe still more. 50. Yes. Right. So I will export this data. So just suppose ASCII files. I have saved my data sequence in queue. So this is the sequence. I will send my file name, my data 1, this be by data 2. So I export my data. I don't have to do anything in this animation. What I will do is I will simply change my data. I will stop this animation, load my data, instead of my data 1, my data 2, run it. Do you see now? The big bob is, I have given more velocity, so now it's moving full circle. Do you see it's moving full circle? See what when it stands, what happens to the smaller one? If somehow or other that big will stand, then it will rotate very fast, the smaller one. Now reversed rotation. See, something happens. Interesting. So is that interesting, guys?
Yes, sir.
Huh?
Yes,
So
sir.
you can repeat that. So if there are questions, you ask me in the next class. Okay. Now you leave. There is some. Now you have almost 10 minutes for your exam. Okay. So I have some hints for your exam. There is a question on equation derivation. You can derive equations to answer that. If you are intelligent enough to look at the pattern, you can actually correlate what should appear where. Even you can use dimensional analysis. Okay. So different ways, without even deriving the equations, you can choose what actual parameter or what actual solution should appear where. Okay. I have kept some spaces blank in ABCD matrices. You have to fill those things. Is that clear?
The remaining question.
Many questions are very easy. They are very easy. No hint required. Okay.
Sir, all are single correct, right?
There are some drag drop questions. Drag drop you will get, if you do partially correct, you will get partial marks. Right. Suppose you have to drag 5 items. From that you have placed 2 of them correctly. Then you will get 4 by 5 marks. If it is 2 mark question, you will get 2 by 5 into 2, 4 by 5 marks. Okay.
But there is no negative marking, right? For
no penalty, nothing, no negative marking. There is no negative marking. Okay, let me stop my recording. Otherwise, these are also getting recorded. Stop recording.